To better be able to understand the number of signals as well as where they will appear in a given NMR spectrum, we need to talk about something called shielding effects. In the last video, I mentioned there are 4 factors that we really think about when we're considering an NMR spectrum. And the first of those you were introduced to a little bit, but we'll keep coming back to this as we learn a little bit more. And that's how many sets of signals you would expect to see in a given NMR spectrum. And so what we're going to learn to do is how to divide up a structure into sets of what we call equivalent protons. We also introduced the term chemical shift. So this is talking about where the signal's going to appear. But we didn't really get into why different protons will show up at different chemical shifts, so that's what we will address in this video. And then in the 2 future videos, we're going to look at what's called the integration, so how many protons are being represented by one signal. And then probably the most complicated of the 4 is what's called the coupling, and that will be in one of the last videos that we cover for NMR. So follow along with me here. Here's this equation that I referred to several times in the first video when we looked at a little bit of the theory as to where the signal comes from in an NMR experiment. And the big take-home message, if you remember, was that the magnetic field strength is directly proportional to the frequency at which resonance will take place. So in other words, where this equation is satisfied. And so each nucleus is, of course, surrounded by electron density. And electrons are moving electric current. And they will generate an orthogonal magnetic field. I hope you probably remember that from physics, that a moving electric current always generates a orthogonal magnetic field. And this magnetic field that we're going to call B local, so there's a key term you need to keep in mind. That's the magnetic field being generated by the surrounding electron density. It's going to oppose the big magnetic field, so the external field that we're calling B naught. And the result of this is that each nucleus does not really feel, quote unquote, or experience the full strength of the magnetic field, the external magnetic field. What they're actually experiencing, so we're going to call this B actual, is the external magnetic field minus the local magnetic field. So this effect, this local magnetic environment sort of detracting from the larger magnetic environment, we call a shielding effect. And we say that the nucleus is being shielded from the larger external field by the local electron density around that nucleus. So let's kind of look at the result of that. Let's say that you have a sample that's not shielded at all, and it's going to experience a certain size magnetic field and create a certain size energy gap. What happens is, if you get some shielding taking place, you now have decreased, remember that this local field is actually detracting from the larger field. So the actual magnetic field experienced by those nuclei is going to be smaller. And so the energy gap now is going to be smaller. And then if you get even more shielding, that energy gap is going to close up even more because the magnetic field strength is actually decreased. So we would say that a completely exposed nucleus that's not being shielded at all would be experiencing the actual full strength of the external magnetic field. So the B actual is the full strength of B naught. But when shielding starts to occur, the actual magnetic field strength is being decreased by however much the local magnetic field strength is around that nucleus. And so as shielding increases, the actual magnetic field strength decreases. And because there's a direct relationship between the magnetic field strength and the frequency that's required to cause resonance, this is a very key point. The frequency that is required to satisfy that equation is actually going down as well. And here's the other key point. When the frequency decreases, that's going to be lower energy. That also means that the parts per million is going to decrease on the actual NMR spectrum. So the chemical shift is going to go down as the frequency goes down, and that frequency is going down as the magnetic field strength decreases. Let's go back to our example of methane versus dimethyl ether and talk about why methane showing up very close to 0 and dimethyl ether showing up past 3. So the chemical shift is significantly higher for this set of protons than for the 4 protons up here. And the reason for this is that dimethyl ether has a dipole that goes toward the oxygen, and the result of this is that the local environment, the local magnetic environment created by the electron density around these nuclei is being decreased. So the electron density is being pulled in this direction, and that means that these 6 nuclei here and here are not experiencing the same external magnetic field strength as these 4 up here, which does not have a dipole. So we would say that this is a more shielded set of nuclei. And down here we have what's called de-shielding taking place. So it's exposed to more of the external field, and therefore you're going to get an increase in the frequency that's required to satisfy the resonance equation, and that's going to lead to an increase in the chemical shift. So the chemical shift really tells us about the local magnetic environment of a given set of nuclei. And so we can tell if a nucleus is highly shielded or de-shielded because that's going to result in a different chemical shift. And anything that pulls electron density away from nuclei is going to be what we call a de-shielding effect, to expose it to more of the external magnetic field. The opposite, of course, would be anything that pushes electron density toward those nuclei is going to make them more shielded. But let's talk about what can cause de-shielding. We saw the inductive effect on the last slide, having dipoles. So if you look at the halogen series, for example, the more electronegative the atom is at this position. So fluorine is the most electronegative, and notice that the protons right next to that fluorine are actually at the highest chemical shift because they're experiencing the most of the external field. You can see a similar pattern with a nitro group, which is a very powerful electron withdrawing group. But notice that as the nuclei get further and further away from the electron withdrawing group, that the effect of the de-shielding is decreased. So the ones that are closest to the electron withdrawing group are going to feel this effect the most and be exposed to more of the large magnetic field. The ones that are furthest away aren't experiencing that inductive effect quite so much, and so they're actually going to be shielded a bit more. Now that you know a little bit about shielding and de-shielding effects, let's go back to predicting the number of signals that we would expect to see. And so if you take a look at this ketone at the top, you'll notice that these methyl protons being right next to the carbonyl, they're going to experience some de-shielding because of the electron withdrawing nature of the carbonyl. However, the protons on this side, even though they're situated the same distance from that group, having the methyl group here makes them different. They're not sitting in the exact same local environment as the protons in red. So these are not equivalent. And so overall, we would actually expect to see 3 signals here, one from the red, one from the blue, and one from the pink. If we take a look at the ether down here, we have 3 protons that are on a carbon that's directly connected to the oxygen, which is the electron withdrawing group. Over here we have a blue proton that's also on a carbon that's neighboring, but these methyl groups are affecting the local environment as well. So the red and the blue protons are not equivalent. And then you have these 6 pink protons, which are the same distance from this oxygen here. If we were to count in sigma bonds, it looks something like this. And so you have 1, 2, 3 sigma bonds away. All of these protons are in the same position, and their orientation in space is the same as well. And so they're experiencing the same magnetic environment. So once again, we would expect 3 signals from this ether. We can kind of divide up the NMR spectrum based on where different functional groups tend to show up. And notice that these are regions, so these are not borders that are set in stone here. You can have fluctuation in terms of where these groups show up, depending on what else is on there with it. But these are rough ideas. So generally the most de-shielded type of protons, the ones that are exposed the most to the magnet, are going to be aldehydes and carboxylic acids. They show up way down past 9, sometimes even close to 12. Next in line we have the benzene protons, and we're going to talk a little bit more about why they show up so far down, as well as the protons that we call vinyl protons that are directly on a double bond. Halogens tend to show up in this region here between like 3 and 4. Protons that are on a carbon with a halogen on it is what I mean by that. And then allylic protons, so these are 2 new terms for you. Vinylic is directly on the double bond, and allylic is on the carbon next to the double bond. And those tend to show up, around like 1 to 2. And then completely saturated with no de-shielding effects are going to be the ones that show up at the low energy end, the most shielded. And so they're going to be between 0 and usually between 0 and 1. You can find these types of data tables that show different protons on various functional groups and approximately where they will show up in an NMR experiment. So there's one embedded in the SoftChalk module, and that's on Blackboard, and that will be the one that you're given for exams. There's also another one in your textbook. The one here is an abbreviated version, but it kind of gives you an idea of what to expect when you're looking at a table like this. The protons that are highlighted are then you're given a shift value for about where they normally show up. Keep in mind that these can fluctuate depending on what else is in the structure. So don't ever think of chemical shifts as being set in stone. They can move around, especially when you get to NH and OH type protons. Notice these have a very wide range, and that's because of hydrogen bonding and pH effects there. And then, as I mentioned, the carboxylic acid and aldehyde are very far down. And we're going to look at why the benzene protons show up where they do. Before we go any further, let's try a little exercise. Let's see if we can decide how many signals we're going to see, and then which set of signals is going to be the most shielded or de-shielded. If you take a look at the 3 protons here, they are not in the same environment as these 3 protons there. Hopefully you're able to kind of see that by now. And if we were to count the number of sigma bonds, so what we actually have here, remember, is CHO. So these 3 protons are all 2 sigma bonds away from an oxygen. The 3 protons on the other side, in green here, so remember we have this, are actually 1, 2, 3 bonds away from an oxygen. So I would anticipate that the sigma bonds on this side are going to be more de-shielded. they're going to be experiencing the effect of the electron withdrawing group more so than the green protons. And so I'm going to expect this to show up at a higher ppm. And indeed, we have an NMR spectrum that has two signals, with one of them further downfield, closer to 4, and one of them further upfield, closer to 2. And I'm going to say that the signal here belongs to these protons, and the more upfield signal belongs to the other 3 protons. Let's do another one. You can see that there are really kind of 2 sets. So we would call these equivalent protons, those 3, and then we would say that the other 3 are also equivalent protons. So I would expect to see 2 signals. And in terms of shielding or deshielding, these protons here are, if you count in sigma bonds, this is what we have going on. They are 1, 2, 3 sigma bonds away from an oxygen, versus the protons up here, which are on the carbon that's directly connected, and these are only 2 sigma bonds away, so I would expect these to be more deshielded, and so they're going to show up at the higher ppm. And again, we do have a spectrum with 2 signals, and we're going to say that the more downfield signal is coming from that methyl group, and the more upfield signal is coming from the other 3 methyl groups here that are less deshielded. Let's talk a little bit about why the benzene protons show up so far down, and it's an effect called diamagnetic anisotropy that's going on. Essentially what's happening is, if you think about a benzene ring, okay, so what we have here is this. Really, there's 2 resonance structures that you could draw for this benzene. And so what you have in actuality, if you were to look at the resonance hybrid, is a circulating set of pi electrons. These 6 pi electrons are kind of zipping around in this circular motion around the ring. And that creates its own electromagnetic field. And it turns out that that field actually reinforces the external field. So instead of having the B actual here equal B0 minus B local, so this is deshielding. Oops, this is shielding. What we're looking at is a case of B actual equals B0 plus B local. And this is a deshielding effect, because the local environment is actually intensifying the external field. And it only does this because of the position of the protons. They happen to be sitting in the correct orientation to be hit, so to speak, by the magnetic field being generated by these electrons in the benzene ring. So it's because of their position in space that this magnetic field is getting reinforced. The same thing happens down here with vinyl protons, so protons that are directly on an alkene, but it's just not as intense of an effect as the benzene, and so the protons of benzene show up between 7 and 8 ppm, and the protons of a vinyl group are somewhere between 4 and 6 ppm. They're just not as deshielded. The aldehyde proton, though, so something like this, is very deshielded. We saw that this shows up between 10 and 12, so this anisotropy effect is actually very strong on the aldehyde proton. It should be mentioned that although alkynes do have overlapping p orbitals, of course, that's the triple bond, and they do have their own electromagnetic field associated with them. What we don't see with the alkynes is this anisotropy effect, and that's simply because the protons on an alkyne are not situated correctly in space. So remember, this is a linear molecule, and these protons are not going to be in the correct spot, basically, to feel the effects of this magnetic field. So there's no anisotropy here. So there's no reinforcing of the external field, and so these guys show up closer to like 2 to 3 ppm. They're fairly shielded. Let's do another exercise predicting the number of signals in the shift, and this is just plain benzene. Benzene, as we saw, is going to give signals. The protons on the benzene are going to give signals between 7 and 8 ppm. And there's no reason why any one of these would look any different to the spectrometer. They're all in the same environment, so we would predict one signal here. And indeed, that's what we see. So here's the one signal between 7 and 8 ppm for all 6 of those protons.